In this video, I want to talk a little bit more about these ideas of partial derivatives. To start with, I just want to calculate a bunch of these things. So we'll look at this function, x squared y cubed plus x multiplied by the sine of 2 times y plus y multiplied by the cosine of 3 times x. There are going to be two first-order partial derivatives. When I'm thinking of the partial derivative of f with respect to x, I think of the x as the variable and pretend that the y is a constant. So I'm just going to write out the usual derivative ideas, except in the back of my head I keep saying to myself, y is a constant. Now that means that y cubed will be a constant, sine of 2y will be a constant, and that factor of y will be treated as a constant. If I can keep that context straight in my head, then this is actually easy. The first term is x squared times a constant. The derivative would be 2x times that constant. The next term is x multiplied by something I'm treating as a constant. The derivative would be the constant. Y is a constant factor in the last term. The derivative of cosine 3x, given that x is the variable, is the negative of sine of 3x multiplied by 3 from the chain rule. So the last term is minus 3y sine of 3 times x. When we look at the partial derivative of f with respect to y, we have to change our perspective. In this, I'm going to pretend that x is a constant and that y is the variable in the problem. So in a moment when I say the derivative, I mean the derivative with respect to variable y, not x. This is the constant x squared times the third power of y. That'll be easy to do the derivative of. This is the constant x multiplied by sine of 2 times the variable y, and this is the variable multiplied by something that in this context I'm going to treat as though it was a constant. All I have to do in order to calculate these things is maintain the correct perspective as to what is being treated like the variable and what's being treated as a constant. This is a slightly more complicated problem. I'm going to think of a rational function, ratio of two polynomials. F of x and y is going to be 2x plus 3y divided by 1 plus x squared plus y squared. Regardless of which one of the x and y that I'm thinking of as being the variable, I'm going to have to use the quotient rule on this. I'm going to write out more than I probably need to, but I want to be clear about this. The quotient rule says I should write down a fraction. The top of the fraction is the bottom of this function times the derivative of the top, derivative in this case meaning partial with respect to x, minus the top times the derivative of the bottom in the same context, divided by the square of what used to be on the bottom. Keeping in mind what's being treated as a variable and what's being treated as a constant, to get the partial of f with respect to x is just a straightforward calculus 1 type calculation. To find the partial derivative of f with respect to y, I do practically the same thing. I have to use the quotient rule again, so it's bottom times the derivative of the top minus top times derivative of the bottom divided by bottom squared, except that the context has changed now. When I say derivative up here in the top, I mean I'm going to think of y as the variable and x as being a constant. Just as before, if I can keep the context correct, then this is just a Calculus 1 problem. It looks a little weird because we're so used to thinking of the variable as being x, but if we can get past that, this is not very difficult. A commonly seen alternative notation for partial of f with respect to x is f with an x as a subscript here, and partial of f with respect to y is sometimes written as f with a subscript of y. Generally speaking, if I have a symbol and I've got a subscript on it, we'll interpret it this way. Using this new notation, I can figure out the partial of f with respect to x and partial of f with respect to y in the same way that we've done previously. Hopefully, because of the preceding comments, there's absolutely no mystery about where these things are coming from. In the first semester, it was often useful to look at the second derivative also, because that described the concavity of the graph you were looking at. Commonly seen notation is the Leibniz dy dx style notation. Also commonly seen is f with an x, indicating I did the derivative of this function in terms of its variable x, and then later did the derivative of that with respect to x as well. Just as with these, in the case of partial derivatives, we'll have higher order partial derivatives. However, because I have two first-order partial derivatives, and each one of those typically depends on two variables, there's actually 4 second-order partial derivatives that I could look at. I could differentiate with respect to x first, and then with respect to x again, x first, and then differentiate with respect to y first, and then take the derivative with respect to x, or do the derivative with respect to y, and then differentiate that with respect to y. We're going to have 2 commonly seen notations for this. One of them is similar to this notation. What we'll do is we'll think of the order in which we see things visually here, and we'll just copy that. In the case where I'm differentiating with respect to the same variable both times, we'll use a familiar-looking notation. We use the curly d instead of the regular d to remind ourselves that these are partial derivatives. I'd say the second partial derivative of f with respect to x. In this one, I'm differentiating with respect to x first and then y later, and when I see the symbols, I just write them down again as they appear here. I'd pronounce this as the second partial derivative of f first with respect to x, then with respect to y. Likewise, in this one, y is the thing I differentiate with respect to first, and then later do so with respect to x. Second partial of f first with respect to y, then with respect to x. And lastly, if y is the variable of differentiation both times, we use the symbol that you would think we use, second partial of f with respect to y. There is an alternative notation that we can see also. If I wanted to be literal-minded about it, I could write f sub x as partial of f with respect to x, and then indicate that I want to do the partial derivative of that with respect to x by putting another subscript of x on. Likewise, second partial of f first with respect to x, then with respect to y. You do the derivative with respect to x first, later do with respect to y, and likewise. What people usually do is they leave the parentheses out. This sometimes seems troubling because in this one, visually, the y comes first and the x comes second, while here, visually, it's the other way around, and likewise for that one. This is just a notational issue. The variable name that is closest to the f is the one that gets done first. If you keep that straight, this notation isn't as strange as it looks. What is strange, though, is that it looks like there's going to be 4 of these things, but it turns out if the function is even reasonably nice, there's really only 3 of them. As an example of this higher order derivative business, I'm going to look at the function f of x and y equals x cubed y to the 4th power. In order to get the second derivatives, I'll need to know the first derivatives, of course.
Of course!
I'll write down what I'm going to calculate, and then we'll talk our way through it. To get the second partial derivative of f with respect to x, I'm going to look at the partial derivative of f with respect to x, that is to say 3x squared y to the 4th, and differentiate it, thinking of x as being the variable. To get the second partial of f first with respect to x and second with respect to y, I'm going to differentiate partial of f with respect to x, this same function, except this time I'm going to think of y as being the variable and x as being a constant. This one, first I'll look at the partial of f with respect to y, which is that quantity. I'll think of it as a function of x and take the derivative. And lastly, I'll look at the partial of f with respect to y, this quantity. Think of it as depending only on y. As we'll see shortly, this quantity has a fairly direct interpretation. This quantity does as well, but these two really don't. Nothing like this ever happened to us in the first semester of calculus or in the second semester. Also, an observant person will notice this is 12x squared y cubed, and this is also 12x squared y cubed. It could be that that's just a coincidence, but it turns out that it isn't. If the functions involved are reasonably nice, these mixed second partial derivatives will always be equal to each other. I want to stop for a moment and think about what all of this is supposed to mean. I'm thinking of the graph of function f of x and y, which would be z equals f of x and y. Down in the xy plane, I have some input point into my function. The z-coordinate on the graph will be the function value of f that goes with that point. So I'm going to have a point of my surface, x-coordinate a, y-coordinate b, and z-coordinate f at a comma b. I first want to think about the partial derivative with respect to x. In the definition, I look at a difference of function values, but I hold the y-coordinate constant and let the x vary. So When I'm thinking of the partial with respect to x, I'm not thinking about all points down in the xy plane. I'm only thinking about the points that I get when the y coordinate is held constant to b. This means I'm not thinking about all of the points of the surface. I'm only thinking about the points of the surface that lie above this straight line. For each point on this straight line, there's a function value, there's a point on the graph to go with it. So every point on this line is going to produce a point on the graph. All of those points on the graph have y coordinate equal to b. So this arc lies in a plane that is parallel to the xz plane. I've drawn it separately here because of my atrocious drawing abilities. The positive x direction is this way, so what I'm going to do is I'm going to pick this picture up and turn it and lie it down on the plane of the paper so that the positive x direction goes off to the right, which is how we usually draw this kind of thing. So this is the graph of an ordinary calculus 1 type function. If I keep the y constant, z is a function of x only. This graph is an ordinary curve. It has a slope of its tangent line at this spot. If I think of z as just being a function of x, since y is being held constant, the slope of this tangent line is the rate of change of z with respect to x only. That would be the partial derivative of f with respect to x. So in a perfectly reasonable way, this partial derivative is the slope of the surface in the positive x direction. Likewise, since we have only a single independent variable in this picture, the second derivative of z with respect to x, which would be the concavity, is the second partial of f with respect to x. In the same way, the partial derivative of f with respect to y is the slope of the surface in the positive y direction, and the second partial of f with respect to y is the concavity of the surface in that direction. So we can interpret these things that we're calculating in the following way. Partial of f with respect to x is the slope of the surface in the x direction. Partial of f with respect to y is the slope in the positive y direction. The second derivative of f with respect to x both times is the concavity in the x direction. This is the concavity in the y direction. But there are also those other two second derivatives. At the moment, we have no idea what they represent to us. A reasonable person might be thinking, this tells me the rate of change in the x direction and the rate of change in the y direction. Assuming that my function isn't too badly behaved, is that enough information to tell me the rate of change of f in any direction? It's going to turn out that the answer to that question is yes. We'll see that later. Also, this is the concavity in the x direction, the concavity in the y direction. Is that enough information to tell me the concavity in any direction? The answer to that question turns out to be no. I need to know about these things as well. This has been my second video on the idea of partial derivatives. I hope that this is clear enough so that everyone can easily understand. In the meantime, I hope everybody's having a good day. I'll talk to you again soon.